Okay, everybody. Today we're gonna talk about the common collector amplifier. The common collector amplifier is also known as the emitter follower amplifier. As you probably know, the common collector amplifier has no voltage gain, but it has high current gain. And today we're going to try to explain why it is useful to use the common collector amplifier even though it has no voltage gain. So first let's look at what happens if you try to connect a signal source. So it's shown on the left with that red box. So you have a source, a sinusoidal source, VSOC. OC means open circuit, because there is a internal resistance attached, RSINT. So the VS is 200 millivolt peak to peak. So it's a AC signal, and you have an internal resistance, which is, for instance, 10k ohm. Here I'm gonna look into a signal source with a pretty high internal resistance, because this is where you want to use a common collector amplifier when the signal source has a high internal resistance, in this case 10k ohm. For instance, if you use a microphone, that would be the case. So you have your signal source with a high internal resistance, RSINT. Now, if you try to connect this to a loudspeaker, a speaker, which is seen on the right in that red box, and the inside of that red box is basically a speaker, something with a very low impedance. So it's low frequency, pretty much resistance. So it's called RLD, R load, and it's 16 ohm in this case, could be 8 ohm or whatever. And the voltage across is VLD, V load. And the inverted triangle is the ground. So if you use the voltage divider rule, the V load is equal to Vs times RLD divided by RLD plus RS. So in this particular case, it's going to give you a voltage V load equal 0.3 millivolt peak to peak, which is not going to be able to drive a loudspeaker for sure. So this amount of voltage is unusable. So what you want to do is you want to replace that red box on the right with a common collector amplifier. Okay, so let's look at the next slide. Okay, so here it's the same idea. You still have that signal source on the left, 200 millivolt sinusoidal, and you still have that large internal resistance, RS, but now you're connected to a common collector amplifier with a Rin is an equivalent AC input resistance. Okay, and with the common collector amplifier is such that Rin, so the resistance that you see when you look into the amplifier, so that Rin is much larger than the R load from before. In our case it was 16 ohm. It was 16 ohm. So that was 16 ohm here. So R in is going to be much larger than your R load. So again, if you use the voltage divider, the V in, which is the voltage across, is going to be equal to Vs times R in divided by R in plus Rs. And what you're going to get is a usable voltage amount to drive the speaker. So that's the whole point of using a common collector amplifier. You don't get a gain in the voltage, you get a gain in the current. So because the source has such a high internal resistance, very little current goes out. So that's why you want a current gain. So what happens is that if R in is large, the voltage Vs doesn't drop too much across the terminals of your amplifier, and you get a usable voltage amount. Okay, so even though there's no voltage gain, because of the current gain, it's very useful to use the common collector amplifier in this case when the signal source has a large internal resistance, like a microphone. Alright, so let's continue. So how do you, okay, let's look at first at the common collector amplifier. Let's see if I can. Okay. Okay, so that's a lot of stuff. So what's in black, it's coming directly from the book called Practical Electronics for Inventors by Paul Schertz and Simon Monk. I highly recommend it, although he doesn't go into a lot of details about how he gets the equations and stuff. So here I'm going to try to explain. Okay, so let's look at the circuit. So you have V in, so this is the AC source. So no DC, so this is pure AC. Of course, there is the setup voltage divider R1, R2 to set up the biases. But I'm not going to talk about that. I assume you know about it. Of course, you have a capacitor C1 to block any DC coming from the source. This point here, this is the base of the transistor. It's also where V in is computed. So that's V in right there. You have the base, collector, emitter. So here there's no resistance on this path, the collector path from the DC source over there. And of course you have now you have RE, which is if you remember the common emitter, you had an RE here because for stability purposes, here it's not for stability. You need something here, RE. So what else? Okay, so and the output. So you have the RE, and then you have a coupling capacitor C2, which is going to block the DC. So you get the V out, which is pure AC. And what you're going to see is that V out is almost identical to V in. V out is slightly lower than V in, and it's in phase. So V out follows V in. So this is why the common collector amplifier is also called emitter follower. Okay, because V out follows V in. Okay, so here I'm going to talk about voltage gain. So the voltage gain is about 1, a little bit less, and the current gain is much greater than 1. Of course, so that's why we use a common collector for the current gain. Okay, so there's a resistance that's important. So this is the R in base AC. So this is the equivalent AC resistance that you see looking into the base. So if you look into the base, this path towards ground, this path towards ground, this is that resistance, and we need it to compute the Rin. But I'm gonna go into detail how you get this formula. So Rin base AC equal HFE, which is beta, the transistor gain. Re is here, the R load. So basically this is Re parallel with R load. Okay, but let's look into how you compute that thing. Okay, so how do you compute Rin base AC? Okay, so here's our setup. So you have the transistor here, so you have the base, collector, emitter. So IB, so this is the base current which goes from B to E. It's usually small. Of course you have the collector current, the IC, which goes like this, and you have the emitter current, the IE, which is equal to the sum of the two, so IE equal IB plus IC, and as you know, it's IB plus IC is slightly larger than IC, but we assume it's equal to IC, so IE equal pretty much IC. So here the emitter resistance, I call it Re prime, because if you go back to the previous picture, we don't have just Re, we have Re in parallel with the load, R load. Okay, Re in parallel with R load, so that's why I call it Re prime. But if there's no load, it's just Re. So how do you compute that thing? So if you look at the voltage at B, which is VB, VB is equal to Rej times IB. So Rej is that internal resistance between the base and the emitter, but since it's usually very small, I'm just gonna ignore it. So VB equal, so I've ignored it, so then you have this one, the VE, so this is Re prime times IB plus IC, and as we said before, IB plus IC is almost equal to IC, and IC is equal to beta IB, beta being the gain of the transistor. So VB, the voltage at the base, is equal to beta times Re prime times IB, the current through the base, which means that Rin base AC is equal to beta Re prime, and since Re prime is Re in parallel with R load, Re prime is equal to Re R load divided by Re plus R load, which gives Rin base AC equal beta Re times R load divided by Re plus R load. So if we go back to the previous picture, that's what we have here. So Rin base AC, HFE, which is beta, Re R load divided by Re plus R load. So this is important so that we can compute the Rin. Okay, so we just did that one. So now, how do you compute Rin? How do you compute Rin? Well, it's pretty easy. So this is the setup. So the source is somewhere here. Okay, it comes through here. So this is the base, the B. So you have the current goes, it can go through three possible paths. It can go through the R1 path, the Rin base AC path, or the R2 path. So which means that, okay, and also, so all those paths goes to ground, except here where it goes to VCC. But VCC is a DC voltage terminal, And as you probably know, a DC voltage terminal is like a ground for an AC signal. So this VCC for the AC signal is basically a ground. So this is basically a ground for the AC signal. So now it's pretty obvious that I mean, you can redraw this thing as this. So you have R1, R2, okay, so this is B, and this is the ground, and this is the R in base AC. So now I'm sure you can see that the R in B to ground. Okay, the R in is R1 in parallel with R2 in parallel with R in base AC. So that's how you compute R in. It's very simple. So then when you go back to that thing here you have 1 over R in equal 1 over R1 plus 1 over R2 plus 1 over R in base AC. Well, it's because when you look at the whole thing, when you look at the whole thing and you want to see the equivalent, the AC equivalent resistance from B to ground, you see R1, R2 and R in base AC in parallel. So that gives you the equivalent AC resistance R in, this formula here. Okay, so again, R in is in parallel with R1, R2, R in base AC, and this is the equivalent AC resistance seen when looking at the amplifier into the base of the transistor here. Okay, so you have V in and R in. So then this, when you look at this box here, this is the amplifier. So that's the R in we just looked at, and that's the V in. And the voltage divider rule tells you that V in equals Vs times R in divided by R in plus Rs. And because R in, because it depends on your circuit, but R in is going to be much larger than RLD, 16 ohm, 8 ohm, 4 ohms, whatever. So this shows you that so this RS is 10K, but the R in is going to go up, let's say, to 1K. So it's going to be so this R in is still low with respect to RS, so you can say that this is about equal to Vs times R in divided by Rs. So here, because R in is much larger than R load, let's say at least 100 times. So now your V in is going to be 100 times or 1,000 times larger than what it was when you were connecting directly that source with high input resistance into the load, which was a low resistance load or low impedance load. Okay, so I think I'm going to stop here. So this video showed how when it is useful to use a common collector amplifier, even though it has no voltage gain. So no voltage gain, you would think, oh, it's completely useless, but in this case it's very, very useful. So I think I'm gonna stop here. If you like this kind of video, please like, comment, subscribe, and I will make more. Bye bye.